All right, guys. So this is going to be the lecture for chapter 12, which is going to be basically on waves and mostly on mechanical waves. So we're going to talk about what waves are, which we can see from this picture is an example when, let's say, you have a still water, you drop something, let's say you drop a rock into the water, and then what you get here, you get those ripples, right? So you get basically a waves generated. That means what you have here is you create a disturbance, and the disturbance is basically the source of the water waves, okay? And those water waves are mechanical disturbance because you actually, uh, disturb that by another source, and that's basically called a mechanical wave. So we're going to talk about, let's say, the difference between, or what defines something to be a mechanical wave in a little bit. But what we have here is you can see that, at the center, you see the source for that, disturbance. And then what you see here is then the wave is basically traveling along those, so basically in this direction, that means away from the source, right? Away from the disturbance in basically all the direction. So pretty much radiates, you can think of like, let's say, in the entire plane of the water. And one thing we do see here is those are repeating shapes, which basically are the waves that are moving away from the disturbance or the source, right? With some velocity of the wave. All right. That means what we get here is the wave is basically a disturbance in some kind of medium. And the wave then when it's propagating, it usually propagates with some velocity v, okay? And there are some very unique properties that we're gonna be able to see for the waves, okay? So there are different types of waves. Let's say right now we are considering, for example, a mechanical wave. And mechanical wave is basically a type of wave where there's a medium that, allows the wave to propagate. That means, for example, there would be no water wave without water. And same thing, for example, here you have, let's say, a string. Well, string, if you oscillate the string up and down, you then create a wave, right? It calls a pulse in this case, right? So that wave then will be propagating, you can see, right, to the right with some velocity v. The medium itself, right, kind of goes, up and down, but then you generate a wave. Another type of wave that we're gonna consider in physics 7 is electromagnetic wave. An electromagnetic wave does not require a medium because electromagnetic wave can propagate in vacuum. And the best example of electromagnetic wave is light. Light can propagate in vacuum. It doesn't need any medium to propagate. So that's why it's not a mechanical wave. But any wave that's technically require a medium to propagate is a mechanical wave. And we're going to be seeing several examples of that. Water wave is a mechanical wave. String wave is a mechanical wave. Sound is a mechanical wave. And what we're going to do here, we're going to see a couple of applications of sound waves and application of a string wave, like, like all those musical instruments like guitar and violin, right? Those are basically string instruments that any type of disturbance generates a music, right? Generates a sound. All right, so then let's say what we do here is this. The mechanical wave, if we are not just considering mechanical wave, you can also break them down into several categories. So mainly we're gonna consider a transverse wave. So again, those are mechanical waves, but so like a type of mechanical wave. So the transverse wave is, let's take this one here, the string. In order to generate a string wave, what we do here, we take the string and we oscillate it up and down. And that up and down motion basically allows the wave then propagate to the right. That means what we're doing here is the medium, which is the string, oscillate perpendicular, you can see, right? It goes up and down where the wave is moving to the right. That means it's perpendicular, right, to the direction of propagation. That means any type of scenario where you generate a wave, but having the medium propagate, or medium oscillate perpendicular to the direction of the motion of the, the wave. This is known as a transverse waves. So you can see, right, transverse waves, require exactly, that perpendicular oscillation relative to the direction of propagation. But then you can have, for example, a different type of wave that you can create where the medium, for example, some kind of fluid, could be air, could be liquid, it basically oscillates, parallel to the direction of propagation. For example, here you have some kind of movable piston. So you push the piston to the right and it pushes the, some of that water inside, and that water then basically moves to the right, and then you pull the piston back. As you pull it back, then what you do here is you create area inside the tube where there's a higher concentration of the water molecules, let's say, and then lower concentration, then higher concentration, lower concentration. And as you basically move the piston, parallel to the direction of the motion, because the wave is propagating to the right, and you are, oscillating the system, toward the direction and back, forward and back. That means, you are oscillating parallel to the direction of the propagation. And that is known as a longitudinal waves. That means longitudinal waves are always when the disturbance is parallel to the direction of propagation. That means you disturb the medium and you generate a wave which is moving parallel to the direction of the disturbance. All right, so you can also have some kind of combination of those two. So you can have, for example, water waves is a lot more complicated because they kind of, combine transverse and longitudinal sort of like, let's say, properties, right? And so that's why we don't necessarily cover water waves in this chapter because they're more complex, but we will see an example of transverse and longitudinal waves because those are, let's say string wave is a transverse wave, sound wave is a longitudinal wave, and those are, nice application of those type of waves. All right, so now let's look at some kind of unique to wave, some properties. So the reason we kind of combine chapter 12 with chapter 11, because when you look at the mathematics of the waves, they're very similar to the simple harmonic motion mathematics. So remember, simple harmonic motion was when system oscillate back and forth. And what we did here is we said that if you look at position versus time graph, what you get here, you get a cosine function, remember, and the equation was x equals a cosine omega t, remember, right? So that was kind of like x as a function of time, which is the position, a cosine omega t. But some similar way you can look at things like this. We have a string, and let's say string is connected to some kind of, oscillator. And then you have the oscillator basically oscillate up and down. That means, perpendicular to the direction of the, let's say, oscillations. And what it does here is it then creates a wave. And the wave here is then propagating, let's say you can see, right, propagating to the right, perpendicular to the direction of oscillation or the disturbance. But one thing you can see here is that the shape of the wave, right, is sinusoidal. And one thing we can do here is we can look at the highest, let's say, position the string will get. We call it a crest. And then the lowest position the string will get, and that's called a trough. That means in a way I can do like sort of coordinate system where then the crest is reaching when the string reaches some, highest positions. Let's use A for that, right? The amplitude, like with the simple harmonic motion. And then trough will be then some kind of negative A. And that means we call this distance, right, as amplitude of this wave. And then you can see, right, the wave then repeats that shape, and it's kind of like a sinusoidal. So that's why we can, assume that, let's say, you can see, right, the simple harmonic of the spring and mass generate a sinusoidal waves in the string, okay? That means this, let's say oscillator moves in as a simple harmonic motion up and down, right? And that, generates transverse mechanical waves in the string that it is attached to. All right. So we have again, so this simple harmonic or periodic waves, right? So the series of drops falling into water produces a periodic wave that spreads radially outward. As I mentioned, right? So if you disturb the water, right, you will then generate a wave which will basically spread, in the entire plane. And now what we have is those shapes, right? Those are now the crests. And then between them, you can see, right, those are the troughs. That means here's a crest, here's a crest, here's a crest, here's a crest. And then one of the things we do here is, if you have a crest, then the distance from one crest to another, we're going to see here, is technically this is known as the length of one wave. Okay, so the wave distance, or the distance between a crest of one wave to the crest of another wave, right, is known as the wavelength, right, or the wavelength, and we'll use Greek lambda for that. So Greek lambda, so this is wavelength. Okay, and it's always in units of length, so generally in meters, because it represents the length between, let's say, two crests. Similarly, it can also represent length between two troughs, because what it does here, so let's say from one crest to another crest, that's one wavelength. From one trough to another trough, there is another wavelength. That means any type of repeating. So I can do from here, from this shape to here, that's one wavelength, because after that, it repeats itself. All right, so let's consider a long tube filled with a liquid, or fluid. Technically, we're going to study this in chapter 13. So fluid is anything that is flowing. So a liquid can flow, that means we call it fluid. And gas can flow, we call it also fluid. That means fluid is a combination of a liquid or a gas. So let's say you have some kind of tube filled with fluid and with a piston at the end. Okay, so if we push the piston in, we compress the fluid near the piston, as I mentioned, in order to generate longitudinal waves. So think like this. What we do here is we take the piston and we oscillate, kind of back and forth, right? And what it does here is it creates more dense region and then less dense region, more dense region, less dense region, right? And those regions then are not, compression is where we call the more dense region, and the rarefaction, less dense region. That means I can kind of model it just like the string wave, for example. So compression is a crest, rarefaction is a trough. So crest, trough, right? And so on and so forth. That means you can still consider this as like a sinusoidal, because this represents high concentration, another high concentration, and between them is basically the low concentration. And distance between one compression to another is then the wavelength. All right, so we have sinusoidal wave, again, is a type of wave produced by a source that oscillates with simple harmonic motion, okay? And remember, the amplitude is the maximum displacement you can have for the certain type of, let's say, medium. Now, one of the things we do here is we have a new type of graph that we're going to consider, and this is y, which is vertical position of the medium or the wave, as a function of horizontal position. That means we're considering vertical position of the wave with respect to the horizontal position. And let's say you can see the shape of this graph, right? And then what we can do here is from one crest to another crest, that's basically one wavelength, right? Or from one trough to another trough, and so that's basically one wavelength. And what we have here is, as a function of time, wave is propagating to the right. So let's say if this crest was right here at some time, at some later time, it is moving from here to there, okay? And that represents, like, let's say this displacement, right? So the horizontal displacement of that crest as a function of time, because it is moving to the right, okay? So the crest have displacement of A, and the trough have a displacement of negative A. That means, positive amplitude and negative amplitude. Remember that amplitude itself is never a negative number. So when we say amplitude, let's say 5 centimeters, it's always positive. So that's why we sometimes, when you're considering a trough, we don't say, here's the amplitude for trough and it's negative centimeters. We say that, the trough has a negative amplitude. That means amplitude always positive. Negative indicates that we're dealing with a trough. All right. So the wave, like simple harmonic motion, is repetitive. That means it repeats over, over time. So then wavelength is the distance spanned in one cycle of motion. Okay. That means, one of the things we can do here is we can assume that as the, let's say we wait a little bit of time, then this wave will go from here to there, and the distance, right, will be then exactly one wavelength. So at time t, the displacement as a function of distance will be given as y as a function of position. So this is a new type of equation, right? Y is a function of position, and this is equals to amplitude, then times the shape of the, graph, which is cosine. Then you have, this is argument, so 2 pi, then x, so that means x is basically some distance, right, divided by the wavelength. Okay, that means what we have here is, so you can say, let's sort of like y, vertical position as a function of time, equals a cosine. So basically what we have here is then this 2 pi over the wavelength, then times x. So in a way, this 2 pi over the wavelength is a quantity that doesn't really change, because we assume that if you have the wavelength, it's the same everywhere. But this x can change because I might consider this point at some later time, it might be here, some later time it might be over there, right? That means in a way, what's changing in this equation as a function of time, position, right? Let me kind of change this as a function of position, right? That's what vertical position is changing as a function of x. That means, for example, if I consider 5 centimeters for this x, maybe it's right there and I have a crest. Maybe let's say 10 centimeters later, right? It's here, another crest. But for example, 12 centimeters, which may be somewhere over there. So then I don't have a crest. That means my y is some kind of value less than the amplitude. Maybe let's say I consider then some, a value of 17, which is right here. Then what I get here is something like that. So another value, right, of the y. So that's why y is changing as a function of x. All right, so similarly, we can look at in terms of how the wave changes as a function of time. And this graph represents y versus time. And what we get here is, again, same sinusoidal shape, but now what we're saying here is that as the wave is moving, so when this crest goes from this time, let's say when the crest is right here at some time t, let's say t1, and then when it goes to here some later time t2, then this delta t is exactly one period, because you're considering the time that this crest will go from here to there. Okay, so that means that's basically a one period. And when there is a period, obviously, then you can always find the frequency. Remember, frequency then is equals to 1 over the period. Well, when there's a frequency, you can also calculate then angular frequency. You can also calculate omega, which is 2 pi f, or is 2 pi over the period. Okay. That means we can now combine the mathematical expression for the y, which is a placement as a function of the position at one time, and the displacement as a function of time at one position. And what we get here is, so this was our first equation, y as a function of x equals a cosine 2 pi x over lambda. And now we have another equation, which is for this graph, where y is a function of time, because this graph gives me y versus t. That means this is y as a function of time, because it equals a cosine 2 pi. Then inside the argument, I have the time dependence, and this is basically 2 pi t over the period. Okay. Now, what we do here is, since we have two graphs representing same phenomena, right? Two equations. So technically we are combining them, we're adding them, and we get this giant equation, okay? So this is then y as a function of both position and time, and you just basically combine those two. And this is using one of those trig identities where you combine cosine and cosine, you get, So like a sine function. So this is a sine. So here this 2 pi is basically thing like this, is y as a function of x and t is equals to a sine. So then you get 2 pi over the period t minus 2 pi over the wavelength times time, x. So you get this equation, but since both terms have 2 pi, you can technically factor out, and this equation basically represents same equation, is just what 2 pi is kind of like factored out. Okay, so that's kind of what we have here. One of the things we can also do, you can see, right, earlier I said that 2 pi over t is equals to omega. So you have this equation. Also here, this 2 pi over the wavelength can be defined as the k, which is wave number, 2 pi over the wavelength. So this is known as a wave number. And it has units of, you can see, right, 2 pi over the wavelength. That means radians per meters. Okay, it has units of radians per meters. That means I can rewrite this equation in terms of that, yx comma t equals a sine. That means I'm rewriting this particular equation because 2 pi over the period is then replaced with omega, then times time, and 2 pi over lambda replaced with the wave number k times x. And this k here is not the spring constant k, it's just it's a different thing. It's a wave number, so make sure you don't confuse those. So it's a wave number, and it's always 2 pi, divided by the wavelength of the wave. Okay, and that's equation, you can see a little more compact version of the, equation above. So generally, this is actually my preferred version of this equation. All right. So another thing we have here in this equation is that whenever you are considering this negative inside the equation, that actually gives you, important information. That negative over there in the equation means that the wave is propagating to the right, okay? So for example, if I come back here and look at this wave, so when I have negative in that equation, that means it has a velocity in a positive x direction. So if I have this as positive, that actually represents a wave that is moving to the left. That means this positive, negative inside the argument actually gives you information about the direction of that wave. All right, so for a periodic wave, each particle of the medium undergoes periodic motion. The wavelength lambda of a periodic wave is the length of one complete wave pattern. And the speed of any periodic wave of frequency f, that means the wave has wavelength lambda and frequency f. So now what we're going to do, we're going to derive equation for the velocity of the speed. But remember, so we already know one thing about the speed, right? We know that speed is equals to distance over time. Remember, right? Now, let's assume that distance is one wavelength. Remember, how long does it take for the wave to propagate that one wavelength distance? Well, it's the period of t. That means the wavelength divided by the period is the speed of that wave. Well, remember, 1 over the t is also equal to the frequency. That means one thing I can do here is I can say, okay, so then it's wavelength times 1 over t, but 1 over t is the frequency, so it becomes wavelength times frequency. And probably this is the more commonly used version of the speed of the wave. But there's one more equation that I can use. So remember, so technically what I have is this, lambda. So we said that the wave number is 2 pi over the lambda. So if I rearrange this, then lambda is equals to 2 pi over the wave number. Same way, we have the omega was 2 pi over the period. So if I come back to this equation over here, where I have the wavelength divided by the period, well, here's my wavelength. So it's 2 pi over the wave number, then divided by the period. You can see, right, if I look for the period, So the period then will be 2 pi over the angular frequency. That means it's going to be divided by 2 pi over angular frequency. Here 2 pi is going to cancel out, and the equation is going to give me omega over wave number k. That means you have 1, 2, and 3 different equations that you can use to solve for the speed of the wave. But this is the most commonly used version, but you can see, right? So you can say V is equals to wavelength times frequency, or it's wavelength over the period, or it's angular frequency over the wave number. All of them represent same, let's say, speed of the wave. All right, so let's look at a couple of examples here. So the sound having frequencies above the range of human hearing, about 20,000 hertz, is called ultrasound. Okay. Now, one of the things we're going to talk about later on is that humans can only hear sound between 20 hertz to 20,000 hertz. That's the audible range. So anything above 20,000 is known as ultrasound. So then waves above this frequency can be used to penetrate the body and to produce images by reflecting from surfaces. So generally, this ultrasound is a technique that is used, by medical professionals, right? To, for example, to scan, the babies, right? So let's say when a pregnant woman goes to the doctor, they can use ultrasound, right, to check, let's say to see, how the baby is, in terms of like, let's say if he or she are healthy and things like that, and then you can use ultrasound, and it's perfectly safe for the baby because ultrasound is just a sound wave. It doesn't have any, let's say dangerous, amount of energy associated with that, but it can give you very practical application where you can basically see the, very useful information about, the health of the baby. All right, so in a typical ultrasound scan, the waves travel through the body tissue with a speed of 1500 meters per second. For a good detailed image, the wavelength should be no more than 1 millimeter. So what frequency sound is required for a good scan? Okay, so it's a simple example because you're given the speed and you technically given the wavelength. And all you have to do here is use that equation that we learned, right? Frequency times wavelength is the speed. And just use this to find the frequency where it's speed over the wavelength. And we can see, right, in order to get a good image, you need to have a frequency of 1.5 times 10 to the 6 hertz, which is 1.5 million hertz. That means in order to get a good, let's say, image, right, we need a frequency that is 1.5 million hertz. And it is ultrasound because anything above 20,000 is considered ultrasound. Right. So here's one more example. So the range of audible frequencies, as I mentioned, is from 20 hertz to 20,000 hertz. So what we want to know here is what is the range of wavelengths of this audible sound in air? That means, let's say we know that 20 hertz is the lowest frequency we can hear, but what is the wavelength for that? Well, remember, we are considering then a sound that is moving in air at more or less room temperature. And for that, we use the speed as 344 meters per second. Sometimes even 343 meters per second is almost also acceptable. That means half of the time you'll see 343, the other half 344. So both are okay. All right, so here's one range, 20,000. Again, using the same equation, 344 meters per second divided by 20,000 hertz. Wavelength should be 1.7 centimeters. That means the size of wavelength, that means from one crest to another crest for a 20,000 hertz sound wave is 1.7 centimeters. Well, if it's 20 hertz, then the wavelength is 17 meters. Well, you can see, right, there's a pattern over there. That means when you're considering high frequency for a sound, wavelength is small. When you're considering low frequency, wavelength is high. That means what you have here is kind of like the reciprocals, right? That means the range of wavelength is from 1.7 centimeters to about 17 meters. Okay, so considering the visible light, now here's the visible light, not the audible range. So is 380 nanometers to 750 nanometers wavelength. That means the wavelength, and this is a light, that means this is an electromagnetic wave. So we want to know what is then the frequency of visible, light at those, let's say ranges, right? Lowest is 380, highest is 715 nanometers. That's the wavelengths. So what will be the corresponding the frequencies? Well, as this guy was the speed of sound in air, then we also have a speed of light in vacuum, technically. Remember, that's usually given as c, and this is 3 times 10 to the 8 meter per second. Now, given the wavelengths, all we have to do is just, okay, so let me kind of do this. So there you go. So all we have to do is just basically use the same equation to calculate, the wavelengths, and you can frequencies, and you can see, right, the frequencies are much higher compared to the sound frequencies, because you have 4.3 times 10 to the 14 hertz and 7.5 times 10 to the 14 hertz. Again, those are very large frequencies, because sound, or light, if you're comparing to them, right? So the light has much higher frequency, but also much smaller wavelength, and definitely much higher speed, right? As you can see, 3 times 10 to the 8 meter per second, considering, like, let's say 3 times 10 to the 2 meter per second, which is roughly let's say 300. All right, so now in terms of then solving problems with waves, like transverse wave, one of the things I will be asking you is to be able to identify some of the terms inside your equations. And let's say get information like amplitude, wavelength, frequency, speed, and so on and so forth. So let's say you have some kind of wave, and this is the equation given for that wave. Okay, that means you have a wave as a function of time. Its equation is 6.50 millimeters sine 2 pi. Then in the argument is t over 0.036 seconds minus x over 0.28 meters. Okay. Now, the way you can kind of figure out some of those terms is by looking at the general equation, where y as a function of x and t is equals to then amplitude, then sine, then 2 pi, then what you had 1 over the period, minus then t over the period, then minus x over the wavelength. So that was the general equation. And as soon as you understand the general equation and what each term represents, if I give you an equation like that, you should be, have no problem picking up some of the things. So if you're comparing, okay, so what is amplitude? Well, this is the amplitude. That means anything in front of the sine function. Well, here's that. That means A here is 6.50 millimeters. That means that's your amplitude. What is the wavelength? Well, look at your general equation. Wavelength is the denominator under the x. Here you have x, and under x, what you get is 0.28. That means wavelength is 0.280 meters. All right, so what is the frequency? Well, here in the graph, at least, you're not given frequency directly. But what you're given here is, you can see, right, you have the period, which is that guy over there. That means, so technically, the period is 0.0360 seconds. But we know that frequency, linear frequency, is 1 over the period. That means 1 of the 0.360 seconds, and that should give us, 27.8 hertz. All right. Well, how about speed of the propagation? Well, now I can find the speed from either wavelength over the period, because I have both, or wavelength times frequency. Again, I have both. All right, so let's do this. So 0.28 times the frequency of 27.8, and then the speed will be 7.78 meter per second. Again, wavelength times frequency, and we get the speed. The last one is the direction of propagation. And if you remember, I mentioned that the negative sign in front, inside the argument of the sign, gives you that information. The negative over there indicates that it's moving to the right. Okay, so that means that that's the direction of the propagation. That means negative means to the right, positive inside would mean to the left. All right, here's another equation. So it's a transverse wave that is traveling on a long string that is under a tension of 4 newtons. The equation describing these waves is given with this function, basically. Now, one of the things we have here is, think like this, so here's a string, all right? So the string then has mass m, some kind of mass, and let's say then what we have here is it has length L, so the length L and mass m, and using those two information, we can calculate what we call linear mass density, which is mass of the string divided by its length. Okay, so mass per length. All right, so so what we want to do here is basically find that, mu, which is mass per length. But we're not given the mass and we're not given the length. So what do? Well, there is another equation, because yes, if I have the mass and if I have length of the string, I can measure those, measurements, right, and find the mu. But if I can't, if I don't have those information, what I can do here is this. I can take the string and I can start oscillating it. And as it oscillates, then what I have here is then string, so when it's oscillating, is basically will be moving with some velocity v, because I generate a wave. And then the wave here, because it's a string, there's a little bit of stretching, and there's a f of t, tension in the string. And we are given that tension. I am given that tension. And this is, let's say, being the v of the velocity of the wave. I can combine those two in an equation, which is speed of the string wave, and this is only for the string waves, is given as square root of tension force divided by this linear mass density. That means I have one equation for the linear mass density, which is a simple one if I'm given the mass and the length. But if you're not given, then there's another equation that relates the, this linear mass density to the speed of the wave and the tension in the string. Because I can then use this equation where if I take the square of both sides, then I get v wave square equals f of t over mu. Then I can use this equation to solve for mu, which is then going to be f of t divided by v of the wave square. And I am given the tension, which is 4 newtons. And if I have the speed of the wave, I can just plug in there and calculate and find the mu. Well, at least for now, we are not given the v directly, but we're given the value or the equation, that you can equation describing this wave. And what we can do here is we can try to see that equation and see if that can give us enough information for us to find v. Remember, I can find v by finding the wavelength and frequency and multiplying them, or wavelength and the period, right, to multiply them and find that. And basically I want to know, can I use those information to find? Or remember, I can also find it by omega over k. So that's another thing I can do. All right, so let's look at this equation. So this equation that has this format, yx comma t equals amplitude, then sine of omega times t minus k times x. So this is that equation. This has that format. From here, I can see that omega is 415 radians per second, and k is 44.9 radians per minute. That means technically I can use those directly to find it. But another thing I can do, which, actually in my slides, you can see the second version. So I can use omega to find, the period. I can use k to find the wavelength, and then use speed equals wavelength times frequency. Or I can find the speed by omega over k, okay? That's another version. So let's do this here in the video. Omega divided by k, and if I plug in all those two values, what I will get here is 9.0 9.24 meter per second. Again, try to do the other version yourself, and you can see that you're going to get the same thing. Anyways, we come back here, 9.24 meter per second squared. Then I can calculate this and get 4.68 times 10 to the negative 2. And the linear mass density has units of kilogram per meter, because how many kilogram, distributed over some meter of length. Okay. And that's the equation for the mu, or, the value for the mu for this particular problem. All right, so a couple of things we're going to look at is what happens for the wave that is traveling when it reaches some kind of barrier. Okay, so we have kind of two scenarios. So imagine here the wave is propagating to the right. So it's moving and getting closer to the barrier, but it's something that is, kind of like, let's say, unmovable barrier. That means it's a fixed point. So when it hits this fixed point, then it has nowhere else to go, so it's reflected back. But when it's reflected back, it actually changes orientation. It's now, you can see, right? It's now a downward. It's inverted. It's moving now in the opposite direction, so moving to the left, plus it has a negative amplitude. Okay, that means whenever the wave, right, reaches a point where there is nowhere else to go, it reflects back, but it reflects back in opposite direction. So you can have another where you actually have this point kind of, let's say dynamic, so it can kind of move. So you can see, right, as you're getting closer and closer and closer to the, to the barrier, this point is free to move and it arranges itself so that when the wave is reflected, so you can see, right, it's not changing orientation. It's going back with basically same, with the same, let's say, wave. Same direction, same amplitude. Okay. Now that's kind of important for the waves, especially for the next few slides, because one of the things we can do here is we can understand that, same thing you can think of like when instead of barrier, think like this. So yeah, now you have, when the wave is moving, then you can have another wave there. So you can actually have two pulses overlapping. And that's very important property that only waves have. That means waves can overlap, and when they overlap, we can say, right, so two waves coming from opposite direction, each wave has amplitude inverted with respect to the other. So let's say, for example, this is +2, this is -2. So positive amplitude on the right, negative amplitude on the left. Both waves are moving toward each other. So when they overlap, what happens here, we call this superposition. So during the superposition, they algebraically combine their, amplitude you can think of. So basically you end up +2 plus -2. So technically you get 0 the instant they overlap, okay? So they can cancel each other. Afterwards, then, you still have the same wave as before. So +2, then another one which is -2, and they just continue moving like nothing happened before. But here, during this superposition, they can overlap. So they can reinforce each other or they can destroy each other. And that's something that only happens to the waves, all right? So that means, for example, if you have something like this, +2, moving to the right, and there's another one like this, +2, moving to the left. See, when they overlap, now you're gonna get +4 amplitude during the superposition, right? You have +4 amplitude. Now you get something bigger, okay? So we're gonna talk about this in a little bit, right? So this is called technically interference. So you can interfere with one another. Because things like this, you take two pencils, right? You move them toward each other, they can never go through each other, right? Because a matter has no way of going through one another. But waves can, because waves nothing but technically pure energy. So they can overlap, they can go through one another, but during that superposition, they can either cancel or they can completely reinforce each other. Okay, so that's kind of like the idea when we have, let's say a string wave that becomes sort of like trapped between two fixed points. So let's say, for example, right? So let's say you have a string that is going to be fixed at, at 2 points, but then you kind of like give it an oscillation on one side. So see the wave moves like this, and then hits the barrier on the other side, but there's nowhere else to go, so it reflects back. So it goes like this and hits the barrier on the other side. Again, nowhere to go, and goes like this. Again, nowhere to go. And then it just basically oscillates like this, back and forth, and you get basically that shape over there. So the wave pretty much is trapped, so that's why we call it a standing wave. So it's called like standing wave. That means it's, it is technically will be maintaining this shape, and let's say the wave kind of goes up and down like this. And now one of the things we can do here is those are known as shapes, right, or segments. So you can see right here's one segment, here's another one. You can change the number of segments by changing the frequency, okay, by changing the frequency. So for example, here is a frequency for one segment. Here, if you change the frequency, you're gonna get 2 segments. Here you change the frequency, you're gonna get 3 segments. Here you're gonna get 4 segments. That means to get more segments, you need to change the frequency. And every time you change the frequency, your wavelength changes and your basic number of segments change. And we're gonna see there's a very good pattern where we can kind of be able to look at all those, let's say, initial frequency, for example, as F1, which is frequency for one segment, and then figure out how to find the frequencies for segment 2, 3, 4, 5, or n number of segments. There's a very good pattern. All right, so let's kind of look at closely to this, to this segments. So for example, when you have this shape, I'm going to be using this picture over there. There are 2 fixed points on each side. So one here, one over there. Those 2 represent position where the string is not oscillating at all. So we call them nodes. So the nodes are points at which the string, doesn't move. But there's one more point right here in the middle, right, where, there's also a node, okay? That means N represents the node. Then the maximum displacement, right, is known as the antinode. So you can see, right, so A is for the antinode, where the points which the amplitude of the string is the greatest. That means, for example, here we have 3 nodes and 2 antinodes. We can also represent number of segments in terms of what we call lowercase n. So here n is 2 because we have one shape and second shape. That means n equals 2 represent number of segments. So technically number of segments always going to be equal to the number of antinodes. So if you have 2 antinodes, n equals 2. See over here we have 3 antinodes, right? 1, 2, 3 antinodes, and 1, 2, 3, 4 nodes. So here's a node, here's a node, here's a node, here's a node. So 4 nodes, 3 antinodes, then this n equals 3. Here, let's say here's one node, another node, and the third one, and 2 antinodes. That means here then you have n is equals to 2, okay? And then here is the lowest one where you have n equals 1 because you have 1 antinode and 2 nodes. So this is known as the lowest frequency or fundamental frequency, we're gonna see, right? And sometimes it's also known as, the first harmonic, okay? So again, going back to looking at this, right? So we have then, here's the shape, and we start with the simplest one where we have just one antinode, or n equals to 1. So one of the things you can see here is, remember, so this is shape of a wave, okay? So if I'm looking at this guy over here, I can see that if I take the distance between one wall, let's say to another one to be length L, in this length L, I have only about half of the shape of this wave, right? That's why you can see, right, this L equals half of the wavelength. But if I'm considering n equals 2, see now I have full shape of the wave. That means L is equals to wavelength, but the way we write it like this. So L is equals to n times wavelength over 2. So you can see, right, since n equals 1, so you write this as 1 times wavelength over 2, and you get that. So then L, when you have 2 antinodes, it's equals to 2 times wavelength over 2. So those 2 cancel out, you have the wavelength. That means you can see, right, you have 1 full wavelength when n is equals to 2. Here you have 1.5 wave. That means L3 is equals to 3 times wavelength over 2. So which gives you 3 over 2, right? Which is 1.5 wavelength. And so on and so forth. So you can see the pattern over there, right? That means the pattern here is number of, segments will then, let's say, if you can see, right, if I rearrange this, so let's say lambda 3 here is equals to 2 L3 over 3. That means you have a different wavelength here, where, for example, for this guy here's lambda is equals to 2 times L. So when you're considering the fundamental, if I give you the length, let's say this guy here is 2 meters, then wavelength here is 4 meters because it's 2 times the length using this equation. Okay, and then for this one, if the length here is 2 meters, then wavelength here is equals to 2 meters because it's equal to the L, and so on and so forth. That means you can see, right, what you're doing here is you're changing the frequency to get different shapes, but you're also changing the wavelength when you do that. All right, so when n is equals to 1, this is known as the fundamental frequency. Okay. Also, you can say that this is the first harmonic. So the first harmonic. So fundamental frequency, F1, or the first harmonic. When n is equals to 2, so then you get second harmonic, because harmonic or basically represents, you can say like harmonic follow the number of order, right? So n equals 2, second harmonic. N equals 1, first harmonic. That first harmonic is also known as a fundamental frequency. Now, we can also use some kind of a music term, which is in terms of overtone. And that's basically, overtone is after the fundamental. So the first overtone is the first one that comes after the fundamental. And the first one that comes after fundamental is basically the second harmonic. So try to be careful here, because some problems can give you in terms of overtone or in terms of harmonics. So let's say if you're given third harmonic, that means you're considering n equals 3. But if you're given, for example, third overtone, then third overtone is n equals 4, because that's third overtone is the third one after the fundamental, which is the fourth harmonic. All right, so then let's look at in terms of some examples, because this standing waves generally, one way of describing what happens when you pluck a guitar string, or play some kind of instrument, right? So because they generate standing waves. All right, so here's an example, right? A piano tuner stretches a steel piano wire with a tension of 800 newtons. Okay. The wire is 0.4 meter long and has a mass of 3 grams. What is the frequency of its fundamental mode of vibration? So mode is another way of saying n. So n is basically, you can think of, is also known as mode. Not node, but mode. Yeah, it's kind of like, a lot of kind of similar things. So n is the node, but, capital N is the node, number of nodes, right? And lowercase n is a mode, which is number of segments. You can think like that. All right, so what is the frequency of its fundamental mode of vibration? That means what we want to find here is F1, right? The fundamental frequency. So what is the number of the highest harmonic that could be heard by a person who is capable of hearing frequencies up to 10,000 hertz? All right, so let's calculate this. So what we have here is, what we're given is the tension, F of t, 800 newtons. We're given the length of the wire, right? Which is 0.4 meters. and we're given the mass of the wire, which is 0.003 kilograms. All right. So, and what we want to find here is using those information, right? We want to be able to then find the fundamental frequency. All right, so let's do that. All right, so here's what I have. We technically, again, so we want to find F1. Remember that one of the ways to find F is from this, equation that we already seen many times. Speed equals wavelength times frequency. All right, so if I rearrange, then frequency is speed over wavelength. All right, now what I'm gonna do here is, in the previous slide, I showed you that wavelength, right, can be related to the length, right, and number of modes. So remember, so one thing we can have here is wavelength is equals to 2 times L divided by N. Remember, I showed you that L is equals to N times lambda over 2. So if you rearrange, then lambda equals 2L over N. Okay, that means here I'm going to replace that. I'm going to say that frequency is equals to, so 1 over lambda, then going to give me N over 2L, then times the speed. Okay, but here's what I have. This is it's a stretch, it's a steel piano. So technically it's a string, right? And the velocity of the string wave is, if you remember, we can also represent it in terms of square root of tension force over the linear mass density, right? That means this is F of N. That means that's my general equation, right? So that's my general equation where, like, let's say F of N is equals to N over 2L times square root of F of T over mu. That means you can always use this general equation. Now, what I want here is F of 1 when N is equals to 1, which means it's N is equals to 1 over 2L, right? Then square root of F of T over mu. Well, I am given L, right? It's 0.4 meters, then times square root of F of T, and I'm given that also 800 newtons. And I'm also given way of finding mu, all right? So I'm given length and mass. And remember, the mu here is mass over length. Remember, so mu is mass over length. That means here I do 0.003 kilograms over 0.400 meters. Okay, so if I do that calculation, then I'm going to get frequency of 408 hertz. Okay, so that's now my lowest frequency, first harmonic or fundamental frequency. That means this wave cannot oscillate with a lower frequency than this, but it can oscillate at the higher frequencies. And what I get here is when it oscillates higher frequencies, then it's going to get, different segments. But what we want to do for part B is find the highest harmonic that we can have if you want frequency that doesn't exist, go beyond, let's say, 10,000 hertz. Okay, that means we want some F of N, where F of N here is, let's say, 10,000 hertz. Now, one of the things we have is this. There's a pattern in the equation. So let's say, think like this. If the fundamental frequency is 408 hertz, then second harmonic will be 2 times the fundamental. Third harmonic will be 3 times the fundamental. Or let's say, some n number of, like, let's say, for example, let's say 8 harmonic, right? Or think like this. So the nth harmonic will be then n times the fundamental, okay? That means what I have here is I can use this equation to find what the n is, right? Because we want to find what is the highest mode. That means if I have the f of n, that means this left side, then I can say f of n is equals to n times f of 1, or n is equals to f of 1 or f of n. That means what we do here is just basically rearrange this, right? All right, sorry guys, I'll reround f of n over f of 1. That means I take 10,000 divided by 408 and try to find this n. And if we do that, we're going to get 24.5. Well, we kind of, ignore the 5.5. So then what we can say here is the highest harmonic we can have for someone for 10,000 hertz, capable of hearing, right, is n equals 24. That means 24th harmonic. We can go all the way to 24th harmonic to hear, a sound. All right. Now, one other thing we have here is, again, this is very unique to waves. It's a concept known as interference, okay? So the interference generally, best can be described in terms of taking, for example, two sound speakers and assuming that, let's say, for example, here's a speaker, right? And it sends a sound like this, right? That means it's a sound that goes as a wave like this, propagates. And then, for example, when there are two sources, let's say source 1 and source 2, okay, then source 2, let's say, also sends a sound. Let's say I'm considering some point of interest, point P. All right, so let me put that point P maybe right here. Okay, that means it also sends a sound wave over there. And what I get here is this. So if I'm considering this point P and I have two sound waves reaching that point P, I can get two things. Because at that instant, when at that point P, those two sound waves are overlapping. Or we can say that there's an interference, they interfere. And one of the things we get here is this. They can either amplify the sound, make it louder, or they can cancel the sound where the sound completely disappears. Okay, remember that's one of the things that says, right? So if you have two waves moving toward each other with +2, +2, they're gonna reinforce each other, right? The instant they overlap, it's gonna be then +4. But if you have two waves moving like this, +2, -2, the instant they overlap, they cancel each other because +2 plus -2, you get 0. During the superposition, they can cancel each other. That means you can get that. Now, so we are basically looking at something like this. And what we're saying here is this. You have two speakers are driven by same amplifier. That means we assume that they have the same frequency and same wavelength. So at some point, so let's call this point P. See, you have this wave coming at point P, and then the other wave is coming at point P. So under which condition basically will they amplify, and under which condition will they cancel? And one thing we get here is this. So it depends on when they cover this distance, let's say D1 and D2, and when they get to this point P, it depends on which part of the, let's say here's wave 1, and here's wave 2. See, when they reach this point P, and they have exactly same part of their wave shape, that means, for example, trough or trough, or example, crest and crest. That means when they overlap with crest and a crest, or a trough and trough. In that case, just like here, right? See, crest and a crest. In that case, they have what we call constructive interference. And constructive interference is basically means that the distance or difference between them is either no change in wavelength or thing like this. So technically, if this one is like this, that means is one wavelength smaller, it will still, when it gets to that point P, there's going to be crest and a crest, right? Because at any other times they are trough, trough, or crest, crest. That means they're going to reach there with the same shape. So it's known as a constructive interference. But when they get to, for example, to the second point Q, so let's say this one comes in with a crest, and this one comes in with a trough. Oh, let me do it like this. Like this, right? Troughs, a crest and a trough. Then that means you can see, right, the difference. So see, if this is a crest, and this is a trough. You can see, right, when it's a crest, there's a trough. The difference between them, so from crest to crest, is a half a wavelength this difference, right? That means what we have here is you get what we call destructive interference. That means they destroy each other. So again, constructive interference, you know, when they reinforce each other, and you know, you have, let's say, crest and a crest, or a trough and a trough, and you get a destructive interference where they can destroy each other. That means you have no sound over there when they are, you know, reaching there or overlap with the crest and a trough. Crest of one wave, trough of another, or trough of one and the crest of another. That means they're gonna then cancel each other. All right, so let's look at this one as well. So this probably can explain a little bit better. So here's what we have. So for example, so you have two speakers, and this works with two sources. So let's say source one, source two. Okay. See, what I have here is this. You have source one sending sound wave. See, this is crest, trough, crest, trough, crest, trough, crest, trough, like that. And then you have another, you know, speaker, source two, that sends sound. And you have then crest, trough, crest. Well, let me kind of, so crest, trough, crest, trough, crest, trough, crest, trough, crest, trough. Okay. And what we have here is, you can see, right, speaker two is technically placed some distance behind speaker one, but that distance here is a wavelength distance. Obviously, you can see, right, if I, for example, bring the speaker two right here, that means they have exactly same position, right? They're gonna send the same wave. That means crest, 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 same as if I would move this speaker two to the back of speaker one, exactly one wavelength of the distance. That means it's going to travel exactly one wavelength when it reaches speaker one. And after that, speaker one and speaker two going to crest, crest, trough, 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 crest, crest, right? They're all going to be, you know, kind of moving together with the same shape. And then what you get here, the microphone detects loud sound. That means they are interfering constructively. That means what we have here is, in a way, this. So let's say this is the distance. Let me do this with this color. So let's say this is the distance, let's call this D1, that speaker one is traveling. And this is the distance, D2, that distance, no, speaker two sound wave is traveling. The idea here is this: if you do delta D, which is known as a path length difference, right? So if you do this delta D, and what you get here is this. See, if I do delta D, remember, if the speaker is right here, that means D2, D1 are the same, so you get 0. And you get constructive interference. But also what I can do here is this. I can move this speaker 2 exactly one wavelength difference, or one wavelength behind the speaker 1, and I can still get a constructive interference. That means then I get, you know, exactly distance as one wavelength. That means D1, D2 minus D1, right? So D2 minus D1 is their difference, which is exactly one wavelength. See, if I move the speaker back where the distance here is 2 times the wavelength, I'm still gonna get constructive because it's gonna come crest, 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 and continues. That means what I'm gonna get here is then I'm gonna get 2 wavelengths. Then you can see, right? 3 wavelengths, still constructive. 4 wavelengths, still constructive. That means as long as their difference here is n times wavelength, where n is 0, 1, 2, let's say it's a, you know, a whole number of wavelengths, right? So see, when n is 0, then delta D is 0, they're next to one another. Where n is 1, then delta D is lambda, so speaker 2 is 1 wavelength behind. Well, n equals 2, delta D equals 2 times wavelength, speaker 2 is 2 wavelengths behind. And what you get here is, this is the equation for constructive. So constructive interference, okay? That means that as long as this delta D, you know, their difference in their length, right, is equals to n times lambda, you can then get constructive. Or you can say, right, if you do n you know, if you do like say delta D over the wavelength and you get, let's say 0, 1, 2, 3, 4, right? Then you get a constructive. The next is here. So again, here's source one. So crest, trough, crest, trough, crest. Oh, let me try to do it again. So crest, trough, crest, trough, crest, trough, crest, like that. And here's the second one. So you can see, right, crest, trough, crest, trough, crest, trough, crest, trough, and like this. And you can see, right, when the speaker 2 reaches the speaker 1, it's a trough and a crest. And when it's a crest, there's a trough. And you can see, right, there are, you know, basically, what sometimes is also known, let's say, out of phase. This is in phase. So you have out of phase. And what you get here is you get, when they get to the speaker, see the trough and the crest. They cancel. Microphone detects little or no sound. Because what you get here is you get the crest of one with the trough of the other one. So why is this the case? Because speaker 2 is exactly half a wavelength behind. That means if I do delta D, so let's say this is D1 and this is D2. So if I do delta D, which is D2 minus D1, right? So D2 minus D1, what I will get here, I will get basically N plus lambda over 2. That, or at least for this particular one, right? You can see, right, their path difference here is lambda over 2 because the distance between them, right, is different by exactly lambda over 2. Now, if I take this one and I move it here where it's one wavelength plus another half a wavelength, then I'm going to still get no sound. If I move it 2 wavelengths plus half a wavelength, still no sound. That means the idea is this: delta D is equals to N plus, you know, 1/2 times wavelength. So that means if I get that, then I'm going to get destructive interference. Okay. That means you have constructive and destructive, and then you get those two equations. Okay. So under which condition you're going to get constructive, under which destructive, you're going to get this. Then, for example, if I'm calculating N for this, right, if I do delta D over the lambda, so over here, I'm going to have to get, let's say, you know, 0.5 lambda or 1.5 lambda or 2.5 lambda or 3.5 lambda. You can see, right, those are all going to be the solution for a constructive interference. All right, guys, so let's look at an example here. So we have 2 speakers separated by a distance of 4.3 meters, emit sound of frequency 221 hertz. The speakers are in phase with one another. A person listens from a location 2.8 meters directly in front of one of the speakers. Does the person hear constructive or destructive interference? All right. That means what we're given here is that they are separated by 4.3 meters. That means this distance is 4.3 meters. And we're told that they are in phase. That means technically they have the same frequency and wavelength. Okay. And it says person is 2.8 meters directly in front of one of them. And let's take it right here, right? That means D1 here is 2.81 meters. And the idea here is this. So when the wave 1 gets to this person, and then wave 2 gets to that person, are they going to, you know, interfere constructively or destructively? Okay, is he going to hear sound or not? And to know that, remember, one of the things we're going to have to do here is basically use this equation, right? Find the D1, D2, do their difference, divide by the wavelength, and see what we get. Are we getting, let's say, N equals 1, 2, 3, or are we getting N equals 1.5, or let's say 0.5, 1.5, and things like that? Because this is going to be constructive, and this is going to be destructive. Okay. That means what we need to do here is we need to then use this equation. N is equals to, so we are given D1, which is 2.81 meters. We also need to get D2. But D2 is not given, but we're given a triangle where D2 is nothing but the hypotenuse. So it's going to be then square root of 4.3 square plus 2.81 meters square, right? And we can then use this to get that D2 here is 5.13 meters. All right, that means this is going to be remember the delta D here is D2 minus D1, so 5.13 meters minus 2.81 meters and divide by the wavelength. All right, so are we given wavelength? Well, not directly, but we're given that there's a frequency of 221 hertz. All right, so what do we do with the frequency? Well, remember, it's a sound wave, and the sound wave is propagating with the speed of 343 meters per second. And then that means I can use this equation where wavelength is speed over the frequency, or 343 meters per second over 221 hertz, to get the wavelength of 1.55 meters. Okay. All right, so we got the wavelength, we got the delta D, and then what we do here is we then calculate this. So 1.55 meters for the wavelength, and then we do this calculation, and what we get here is this. So delta D here is 2.33 meters divided by 1.55 meters. Meters cancel out. Remember, we're going to get the number for N, so we get 1.5. So what is 1.5 in terms of type of interference? Well, remember, 1.5 means it's a destructive interference. That means the person will not hear a sound, okay, or barely any sound or no sound at all. Okay, that means this is destructive interference. All right. Okay, so the last thing we have in this chapter is a concept of the Doppler effect. And the Doppler effect is basically every time, let's say you are standing on a street and there's an ambulance moving toward you, one of the things you will hear is the pitch of the, let's say, siren. And one thing you will be able to notice is that siren, the frequency is increasing to when it's moving toward you, right? So the siren like starts increasing in terms of like, let's say, frequency. It increases when it's moving toward you. But when it passes you, it starts decreasing in terms of its, let's say, pitch, right? So let's say what you get here is increase in frequency when it's moving toward you and decrease in frequency when it's moving away from you. But in reality, nothing changes about the frequency of the siren itself, but it appears to be changing for an observer who's standing on the street and it has a, let's say the ambulance moving toward or moving away. And this effect is known as a Doppler effect, right? For sound is the shift in frequency, or the Doppler effect for sound is the shift in frequency when there is a motion of the source of sound S to the listener L, or both, because you can also have a sound like the siren and you can be moving toward the siren. So that's kind of what you get. All right, so then what we have is this. We can calculate what is the change in what type of frequency then the observer would hear, for the Doppler effect. You can see, right? So the Doppler effect, when both listener and source may be moving. So what we get here is this. So V is the, for the sound speed of the sound, basically. That means the speed at which sound moving in air. And usually what we do here for V, we represent 343 meters per second. That means this is always going to be given to you, okay? That means this guy here, without any subscript, is the speed of sound in air, 343. Then you have VL, which is, what we call here, listener, okay? And you have VS, which is source. Okay, that means if, for example, if you're considering the siren of the ambulance, this will be the velocity at which the ambulance is moving toward you. So technically, then you can have, you know, listener is at rest, source is moving, or source is at rest, listener is moving, or maybe listener and source moving towards each other or away from each other. You can have like different combination. Okay. And here's then what we get. So for a listener L and source S moving along the line, joining them, the frequency f of L heard by the listener is related to the frequency f of S produced by the source as follows. So here's then the equation. F of L, that means frequency that listener will appear to hear, is V plus VL over V plus VS. And that ratio, so basically, so then this ratio is times frequency of the source. Okay. So then what we get here is basically you get different frequency when the source is moving toward you and different frequency when the source is moving away from you, basically, right? And what you get here is, you can write in this equation, V is the speed of sound, VL and VS are the X components of the velocity of the listener and source respectively, okay? All right, so here's then kind of like, you know, what's going on. So for example, you have a listener and you have a source. See, the source generates those, you know, wavelengths, you know, as the sound is propagating, right? So then you have the, you know, the sound waves moving with, you know, you can see, right, those are the crests, okay? So one of the things we have is that you can see, right, a listener moving toward a stationary source hears a frequency that is higher than source frequency. That means, for example, let's say if the source frequency is 100 hertz, the listener, because let's say if the listener is stationary, he will also hear 100 hertz. But if listener is moving toward the source, so the frequency for the listener will be maybe 120 hertz. So they will be slight increase in, you know, frequency that listener will hear. And for example, then here, if the source is moving away from the listener, then you're going to have different source, you know, different, let's say, frequency, right? So you can say, right, when the source is moving away from the listener, the waves behind the source are stretched to a longer wavelength, and that means the frequency will be a little bit less. So maybe frequency of the listener will be, I don't know, let's say 90 hertz, or something like that. That means it's going to be less than, you know, actual frequency of the source. That's why the apparent shift in frequency is due to the relative motion of the source and listener. All right, so this equation is, you know, you have to be kind of approach it carefully, because there are, you know, important things to understand about the sign of the VL and VS. Okay, here's what we have. So you can see, right? So this VL can be positive or negative, okay, depending. So you can see, right? So velocity of the listener, it is positive if from L toward S, okay? That means what you have here is, if you, let's say, you take it from here and you draw a line. So let's say from the listener toward S, right? And if the, let's say the velocity of the listener is in that direction, right? So let's say if the listener is moving in that direction that we define to be the positive direction, because the positive direction always going to be from the, you know, listener to the source, okay? That means VL is positive in this case. But let's say, if, for example, let's say here's the listener moving in this direction, but let's say the source is here, let's say the source is here, then I draw a line from the listener to source. That means this is my positive X direction. Then in this case, VL will be negative. All right, because now the listener is moving in the opposite direction of what we define to be the positive direction, which is always from the listener to the source. Okay. All right, so then same thing with the velocity of the source. It's positive from L toward the source, and negative is opposite. Okay, that means, for example, in this case, you can see, right? So I have the distance from the listener to the source, that means to the right, as positive direction. See, my source is now moving in that direction. That means also to the right. That means velocity of the source is now positive. Okay, that means velocity of the source is positive. So for example, over here, and the velocity of the listener is positive because both of them are moving in the direction that we define to be positive. Again, what we do define to be a positive direction is the direction from the listener to the source. Okay, that's always going to be positive, let's say, regardless the actual coordinate system. Okay, so let's look at an example and be able to, kind of apply this. So a railroad train is traveling at 25 meters per second in still air. The frequency of the note emitted by the locomotive whistle is 400 hertz. What is the wavelength of the sound waves in front of the locomotive, behind the locomotive? So let's kind of do those two. So what we have here is this. So the railroad train is the source, and it's moving at the 25 meters per second. So let's say Vs is 25 meters per second. Now what we get here is this. So let's say, I don't know, let's say here's a train. Okay, like that. And it is moving at 25 meters per second. So Vs. Then let's say there's a speaker there that sends sound at 400 hertz, which means f of s, frequency of the source, is 400 hertz. Now, what we want to know here is this. It says, what is the wavelength of the sound waves in front of locomotive? Okay, that means what we do here is we take some, let's say, observer here, right? So we can just, let's say we have some listener over there. Okay. Now, what we do here is then let's define our positive direction. All right, so positive direction will be here to the left. That's my positive x from the listener to the source, remember, right? So then what I get here is this. So then what will be then Vs? Well, Vs will be then negative 25 meters per second, right? Because it's moving to the right, where my positive direction is to the left. Okay, because that's kind of important. Now, the equation then for the wavelength is this. It's velocity of the sound plus velocity of the source divided by f of s, frequency of the source. Okay. And in this case, what I do here is, this is 343 meters per second, then plus V of S. But because V of S is moving to the right, where my positive direction is to the left, it's negative 25 meters per second, and divided by 400 hertz. Wavelength, then 0.798 meters. All right, that means that's the wavelength that the listener will be able to, let's say, measure. How about part B, behind the locomotive? So let's say in this case, so let's say here's the locomotive, right? So let's say here's the locomotive. So it is moving in this direction, Vs equals 25 meters per second. Here's my listener. See, now I take the direction to be positive from listener to the source, and the source is moving in the same direction, so then this time it's positive, right? So then this is part A, this is part B. Lambda is equals to V plus Vs over f of s, which is general equation. So 343 plus 25 divided by 400. And in this case, we're gonna get 0.922 meters. All right. that means I get higher wavelength because the sound waves will be stretching by the time it gets, okay, to the listener. Where here they're kind of compressing because it's moving, you know. All right, so then part C says, how about the frequency for the, you know, let's say, I don't know, let's call this, I guess, case 1, moving toward the listener, and case 2, moving away from the listener. So let's do this. For the C, I'm calculating f of L, which is V plus, you know, remember, V plus VL divided by V plus VS times f of S. All right, so my observer here is at rest. VL is equals to 0 for both of them. So for case 1, when the source is moving toward, so you can see, right, again, Vs is negative. So what I get here is V plus 0 over V minus, or you know, thing like this. So let me put some values right there. So it becomes 343 plus 0 over 343 minus 25. Then times 400. And that's going to give me basically 431 hertz. You can see, right, higher frequency. For case 2, part B, when it's basically behind the locomotive, is then going to be same thing, right? 343 plus 0 over 343 plus Vs, but this time Vs is positive. And what we're going to get here is 373 hertz. That means we have lower apparent frequency when the source is moving away from you. And that equation basically gives you that, right? So hopefully you guys are okay with this, right? So remember, you take your listener, draw a line from the listener to the source and define that to be your positive direction. And then source velocity or the listener velocity then will be taken with respect to that direction. So either they're positive or negative. And remember, so then you can plug in, right, positive, negative velocities in these equations to calculate, you know, let's say apparent, you know, frequency or the wavelength. That's the general equation for the wavelength. This is then the general equation for the frequency. All right, so that's it for this chapter. So go ahead and watch it, start working on the homework problems, and we'll start then chapter 13 on Tuesday, and maybe even, you know, maybe like even start chapter 14.